Have you ever stopped to think about how your phone knows it's you? Or how a car can just drive itself? It's all thanks to this amazing field called computer vision, and it's moving so fast, it's literally changing our world as we speak. So today we're going to pull back the curtain on a truly massive, mind-bending problem that engineers had to solve to make any of this a reality.
And I'm not talking about some far-off sci-fi future. This is stuff you probably use every single day. You've got self-driving cars trying to navigate city streets. You've got your phone unlocking with just a glance. Heck, even your photo app that can find every picture of your dog, or those crazy AI images you see online. This tech is already here, and it's weaving itself into everything. And this isn't just a tiny improvement. You hear experts talk about it, and they say this is enabling things that were, and I quote, just impossible a few years ago. It's not an evolution, it's a full-blown revolution in how machines can perceive the world around them.
But, to really appreciate just how big of a deal this is, we gotta start with the basics. What are we even asking a computer to do when we tell it to see?
Okay, so the simplest task is something called image classification. It's pretty straightforward. You give the AI a picture, and it slaps one label on the whole thing. The classic internet example is this a picture of a cat? The answer is just yes or no. It's a great first step for sure, but the real world is, well, it's a bit more messy than just cat or not cat.
That's where things get really interesting. We move on to object detection. Now, this is what a self-driving car needs to do. It's not good enough to just know there's a car somewhere in its view. The AI has to find every car and draw a little box around each one to know exactly where it is. That's a much, much harder problem to solve.
And trying to solve that problem is what led researchers to hit a massive wall, a hurdle so big it almost stopped the whole field dead in its tracks. It's called the billion-parameter problem, and it all comes down to the size of the pictures we use.
So what's the big deal, right? I mean, we want our AI to see in beautiful high definition, just like we do. Why would that simple request be so unbelievably difficult for a computer?
Well, it all comes down to the raw data. Back in the day, AI experiments used these tiny little images, maybe 64 pixels by 64 pixels. But today, we're working with images that are 1,000 by 1,000, or even bigger. And that, my friends, is a colossal leap in the sheer amount of information we're asking the AI to deal with. Okay, so let's break this down. For an AI, every single pixel is a piece of information. But it's not just one number per pixel. You have 3 color channels for each one, red, green, and blue. So for that tiny 64 by 64 image, the math is 64 times 64 times 3. And that gets you to 12,288 input features. All right? That's a pretty big number, but it's manageable. A standard neural network can kind of wrap its head around that. That's our starting point.
But remember, we want to use those big, crisp, modern images. So what happens when we do the same exact math for a 1,000 by 1,000 pixel image? Well, that number of inputs doesn't just go up, it absolutely explodes. It skyrockets to 3 million. 3 million individual data points from one picture that the AI has to look at all at once. That's a huge jump. But here's the crazy part. That's not even the real problem.
The real problem, the one that broke everything, happens when you connect all those inputs to the AI's first layer of neurons. See, the network has to learn how important each of those 3 million inputs is. You can think of it like a control panel with millions of tiny little dials or parameters that the AI needs to tune just right. So if that first layer has, let's say, 1,000 neurons, the total number of dials becomes, well, it's insane.
3 billion parameters. That's 3 million inputs times 1,000 neurons. Just think about that. The AI would have to learn the perfect setting for 3 billion individual dials just to take the very first step in understanding one single high-resolution image.
So why is that a total showstopper? Well, 2 huge reasons. First, to train a model with that many dials without it just memorizing the training data, which is a problem we call overfitting, you'd need a truly astronomical amount of example pictures. We're talking more than we could ever gather. And second, the sheer amount of memory and computer power needed to store and calculate 3 billion parameters is not feasible. The whole system would collapse. So that brings us to the big question, the central puzzle. If the straightforward approach is completely impossible, how can any AI learn to see our high-resolution world? We can't be stuck using those tiny, blurry images from the 90s forever. There had to be another way.
And luckily for all of us, there was. The pioneers in this field came up with an incredibly elegant and clever solution, A smarter way for an AI to see, one that completely sidesteps that parameter explosion.
We needed a fundamentally more efficient approach. We needed a system that didn't have to look at the entire image all at once and connect every single pixel to every single neuron. That's the brute force way. We needed a smarter way.
And that solution, the idea that underpins all modern computer vision, from your phone to a self-driving car, is called the convolution operation. It's this brilliant idea where the AI scans the image with a small filter, almost like a little magnifying glass, looking for simple things like edges, corners, and colors first. By building up its understanding from small patterns to big ideas, it never has to deal with 3 billion parameters. It's the hack that made modern AI possible. But how does it really work? Well, that's a story for our next explainer.